Dear students, in this short video, I will be recording the procedure for carrying out finite element simulation of a shaft in torsion. And basically, this is going to help you with your lab in week 13, which will also lead to your assignment too. So please check the details in the D2L. So in this lab, basically what we are going to do, we are going to compare the results of hand calculations and as well as finite element analysis, and it will help you understand that how sometimes hand calculations may be performed in a different coordinate system and the FEA may be in a different coordinate system, and how to relate the values of the two. It will also help you understand some of the intricacies of analyzing a shaft under torsion, and it will then you can apply the same procedure in more complicated cases, but it will basically help you understand that how important it is to validate your basic analysis results uh, whenever performing finite element analysis. Now, the shaft in question, each student will have a different set of parameters. The boundary conditions are same for everybody, so it is basically cantilevered from one side, and it is a circular cross-section shaft, but then each one of you has a different torque depending on your student ID as well as student ID, and so you will have a different torque and different material. The length and the diameter is basically same for all the students, but the case that I will analyze has slightly different length than the rest of you. So please make sure you perform the simulation according to your given data as shown in this table, and then you compare the results as well. Now, as far as the theoretical methods are concerned, based on what we have discussed in the lecture session, you'll be using these torsional formulas to calculate the stresses on the shaft. So because in this case the shaft is simple, so no stress concentration factors or other things like that are needed, and it's a simple matter of evaluating the maximum torque based on the theoretical formula as well as calculating the angle of twist. So I've done this calculation for you, and I'll quickly explain this. So in this shaft, in my case as an instructor, the input torque requirement was 360 Newton meter. Since I am calculating the stresses in megapascal, I first convert this into Newton millimeter. So this is my input torque. Then the value of C, as you understand, is basically the maximum distance from this neutral axis. So that is from the central axis. So basically that's the outer radii of my radius of my shaft. So this is basically 15 millimeter in my case. Then based on this diameter, based on this radius, I will then also calculate the polar moment of inertia. And as I explained in the class, this formula is basically giving you the stress in the polar coordinates. Therefore, based on this formula, the stress along all of this periphery will be same, and that will be your tau max in this case. So that tau max will be then in our case 3600,000 multiplied by 15 divided by 79521.6, which is our polar moment of inertia, is equal to 67.91 megapascal. So this is the maximum value that we will be comparing with our finite element analysis. The other value that we will be comparing in our finite element analysis will be the value of the angle of twist, which, as you can see from this figure, is this angle that the shaft goes through when it is being subjected to this torque. Now, the length of the shaft in each case, in my case is 600, in your case it is 500, and we already know this radius of the shaft as well. So from which we have already calculated the value of J. Now, based on this, we will then calculate our angle of twist by putting all the values. Here, the value of the Young modulus of the steel is 77,000 megapascal. Now you will have to read this value and make sure that you are using the same value for the material as given in SolidWorks. If you don't know where to read this, just wait for the next part of the recording where I will show you when we assign the material in the FE simulation. So I'll show you from where you can read the value using SolidWorks. So actually, in fact, I can even show you that just now by dragging my other window over here. So if you right click on the edit material option, you'll be able to read the value. So you select whatever material that you have in your assigned to you, and then you go and you look into the value of the Young modulus. Here it's being given in pascals, and if you want the unit to be in megapascals, you can directly read it as well. Okay, so with this basically now you can our theoretical calculations will give us an angle of twist in radians, which I then convert into degrees by multiplying it with 180 degrees over pi. So it's roughly around 2.02 degrees in this case is our angle of twist. So we will compare both of these with our finite element simulation. So now in the next part I will explain to you how to carry out the finite element analysis. So for our finite element analysis, we will basically be using SolidWorks simulation in the same way as we did for the problem with the notch under axial loading. So we'll set up a new study, okay, but before that we need to have a part. In this case, our part is basically going to be a simple circular shaft, so it's very easy to draw. So I'll just simply go and use the circle command. I'll draw it on the right plane so that my x-axis is the long axis and my cross-section of the shaft in yz plane. So I will basically just simply use the extrude feature, but you can use other commands like revolve or others to generate the shaft as well. The radius of the shaft is 15 mm, so I'll input the radius, and just to make sure that I've got everything correctly, so I can check the diameter of the shaft. So yes, this is okay, and then after this I will basically extrude this. So after this arrow is showing the correct extrusion direction, which is my x-axis. Length of my shaft is 600 millimeters. So for your case, you please use the value in the table. So with this, now my shaft has been extruded and it is ready for the next step. But before I move on, I also want to create a reference axis so that it is easy for me to basically later on apply the boundary conditions. So I'll use the axis command, and I will use a cylindrical surface as the base for defining my reference axis, which will pass through the middle of my cylinder. If you need to have different points for later on, ease of outputting the values, you can create some virtual cross sections here. But right now, I quickly want to demonstrate this, so I'm not doing any extra steps. At this stage, it will be a good idea to save the model so that you can basically then easily carry on the rest of the analysis. So I'll just call it as shaft winter 25 for our semester. So I've saved the shaft. Now I will set up my simulation by going onto the simulation tab and creating a new study. And in the new study, I will give it a name. I'll just call it as pure torsion, okay, because this is what we are trying to simulate. Although the shaft will be supported as a cantilever from one side, we are not going to apply any bending loads on this, and rather we are just simply analyzing it for pure torsion. Right, so once we have done this, next created the study, and this is a static analysis, so I just chose the static portion. Then the next step is to apply the boundary, apply the material basically. So we will, because without this, the analysis will not know which material the shaft is made from. So I will select the material as AISI 1020. So again, I'm just keeping the units in megapascal for everything. So I'll just say apply for this, and then after that I will close. You will have to choose the material according to the details given to you in the report template. Then after this I will start applying my boundary conditions. So one of the boundary condition is very straightforward. We know that it is cantilevered from one side. So I will take one of the ends, and I will basically select this surface and basically apply my fixed boundary condition on this. So this boundary condition has now been applied. What you will realize, I mean, you can run the analysis with this if you want and check, whether you get the correct results or not. But what you'll find out that there will be some discrepancy in the results, and that is primarily because if you right now, although this end is being fixed, in one of the assumptions of our derivation for the theoretical formula was that this beam is not in under any sort of bending. But if you apply the torque on this end without any further constraint, this is free to basically flex about basically the long axis as well. So, about the z axis as well, and therefore you will have a flexural stresses in the beam as well if you do not put any further constraint. So, because of the rod's self weight. Uh, that will not add significantly to the stresses, but it will add some stresses. So it's better to add a second boundary condition to represent this, which may not be present there in a real situation, but it is basically to help us equate our assumptions of the theoretical model. So I will basically apply a roller slider boundary condition on this surface, which will just simply make sure that the shaft is able to rotate along, but it is not going to bend or move in the any other plane, and it is simply able to rotate along this. So this is the type of the condition that I will apply, so that there is no flexural movement. Okay, so once I have applied the roller slider condition, my boundary condition application is complete. Next is the application of the load. So to apply the load, I will select torque instead of force because I know the torque directly. In other cases, in real life, you may be wanting to apply force on a certain place, and then based on that you can calculate the torque. But right now I'm keeping things simple, and I'm just going to apply to keep everything consistent with my problem that I have solved using hand calculations. I will basically apply torque on this face. I need to specify the reference axis for my application of the torque. So now as soon as I select it, I can see the direction of the torque over there. The torque has to be specified in Newton meters, so this value will be 360. Make sure that you don't enter 360,000 because that was in Newton millimeter. So right now there's only one face, so per item is acceptable, and we'll just select OK and keep the rest of the values on their default options. So now we have basically applied the torque, we have basically set up the analysis, and so our basic analysis setup is complete. In the next step, I will basically mesh the model, and after meshing the model, we'll run the study and plot the results. So I'll to keep the video short, I will basically do that in the next episode of this recording. Thank you.